Welcome back to Statistical Reasoning. We are finishing up Chapter 9, Inferences from Two Samples. Thus far we've done two proportions, we've done two means with independent samples, and today we're going to do two dependent samples or matched pairs. We're going to go ahead and run a hypothesis test running through the entire process, and we're also going to quickly do a confidence interval and what does that mean. We always want to make sure we have a good experimental design. Make sure we're doing an actual experiment or we're planning an observation study. Sometimes it's best to do dependent samples when we can and we match up things rather than using two independent samples. We're going to go ahead and do the hypothesis test and the confidence interval. So we need to make sure of our symbols or our notation. So some of the things we need to make sure we know is for an individual difference, we're going to just use the letter D. For the mean, it's going to be mu, but it is sub d for difference, because we are going to be doing two and we're subtracting them. For the mean value of the sample, we're going to do d with a bar, just like we do x with a bar. Now it's the difference. Our standard deviation will be s with a d, that's how we know it's a difference. And then we are still going to use n for sample size. So a lot of our symbols are still the same. We're just using a D. That'll help us know that we're doing a difference of two samples. So we always have requirements. Our sample data have to be, in this case, they are dependent if we are doing a matched pairs. And so they somehow have to have something that they have in common. A married couple definitely is an easy matched pairs. Twins are an easy matched pairs, but that doesn't have to be all the twins they are. We have to definitely make sure that they are a simple random sample. And then again, we have two conditions. We have to make sure one of them are satisfied. Just like in a individual sample or in the independent samples, our n should be bigger than 30, if at all possible. If that is not true, we want to go through and make sure that our distribution is approximately normal. We may have to do a check with that by doing a normal plot or doing a histogram to see that. Now the thing about this though is that the methods are robust, so your normality doesn't have to be exactly perfect. Now we do have some formulas in case you wanted to do this by hand, though I would encourage technology to do this. So T, if you were doing it by hand, is D bar minus the mean of the difference divided by the standard deviation of the difference divided by the square root of n for the central limit theorem. And then of course you would use the table to find the p-value. If we're doing a confidence interval by hand, it's D bar minus the margin of error, and then of course D bar plus the margin of error. And our margin of error, E, would be found by doing our T critical value times the standard deviation of the difference divided by the square root of n, and our degrees of freedom are still n minus 1. That has not changed. Make sure that we go through and do the things, right? Make sure we verify that they are dependent samples or matched pairs. Go through the things we talked about in the previous slide. Make sure we find the difference if we're doing it by hand. Find the D bar and the standard deviation. And make sure we use the same t-test procedures as if we were doing a single mean. So when we're doing it on technology, you'll even notice that we're going to do a one sample mean instead of using a two sample, because we will be finding their difference. Just like before the confidence interval and the hypothesis test, right, are using the same distribution and standard error, so they are equivalent in a sense, that they would both give us the same answer. Okay, so we're going to go ahead and go on and look at our example. So we are looking at Best Actresses versus Best Actor awards, and our Best Actresses generally younger than Best Actors. Depending on how much you follow the movie scene, you may or may not have noticed that one of them tend to be younger than the other. So we have randomly chosen some years and then looked at both the Best Actor and the Best Actress during those years. Those are what's listed, the 28, 62, and so on. Because they are matched up by years, we're going to find the difference of those, and that's the bottom row that you see. So we're going to test a claim. We are going to test the claim. If actresses tend to be younger than actors. Okay. Now, just like before, well, actually, let's test the requirements first. So, are our samples dependent? Well, the actor and the actresses that are chosen are dependent on the year that they got the award. So, from that standpoint, yes, they are dependent on each other. Are they randomly, simple random sampled? Yes, we're going to go with that. They are the best that we know of. Now, is n greater than 30 or are they normal? Well, definitely n is not greater than 30 because in our case n is only 5. We only picked 5 years. We could have picked more. So we definitely need to check the normality then. So using technology, and I actually use StatDisk, I did a normal quantile plot. And so looking at this, you can see there doesn't seem to be too much of an outlier. I don't have anybody way up on the top here or way down in the corner down here. They tend to follow a straight line pattern except for this one here, but it's not considered a significant amount away from it has to be way different. So we're going to go with that. It is. And remember, these are robust. So that point doesn't have to be perfect in order for this to work. So even though n is greater than 5, we're going to go with that they are fairly normal. So we're going to go ahead and work through this. So we're going to start with our claim. Our claim is that actresses are generally younger than actors. So in symbols, now let's look back at our list real quick. And we have actresses are first and actors are second. So if actresses tend to be younger than actors, then it's the smaller number minus the larger number. So we would think that we're going to get negative numbers. So if we're thinking about it in that standpoint, that we're going to get negative numbers if actresses are younger than actors, then the difference in their mean should be less than 0. That makes actresses younger than actors. So that's our claim. So then our hypothesis, our null, is always that it is equal to 0. That means there's really no difference between the age of actors and actresses. And then our alternative is our claim in this case, that it would be less than 0 because the actresses are younger. So this is the claim that we're going with. Now it did tell us in the problem to use an alpha of 0.05. It's not critical to life. So we are going to do a t-distribution or a t-test. I'm actually going to write t-test instead of distribution. Okay, so go ahead and you would grab your technology at this point and put in your data. You would go ahead and not put in all of this data. You would just put in the differences into your column, into your calculator, and then we're going to run a t-test on it. And so when we do that, we should get a t-value of negative 1.557, and that is an approximation, it is rounded, and a p-value of 0.0973. So that is what I got. Hopefully that's what you got when you ran it. So if we compare our p-value to our alpha level, we have 0.0973 compared to 0.05. Our p-value is definitely greater, therefore we failed to reject the null. Okay, So now we have to make our statement. Since we are failing to reject the null, there is not sufficient evidence to support the claim that best actresses are younger than best actors. Okay. Now, even though that we got some negative numbers here, right? 4 out of the 5 were negative, it's not significant. And that's what we always have to remember with this when we're making our testing, that it has to be significantly different. It just can't be different. So let's look at our actual confidence interval and see what it is. So if we think about it, this tells us it's a 90%. How would we know that already on our own? So remember that when we were running our test, we were doing less than, and our alpha level was 0.05, and our test was less than. So it was a one-sided or one-tailed test. Well, that means that the 0.05 has to be on both sides when we're looking at the actual confidence interval. So if I have 0.05 on each end, 5% and 5% is 10%, which means I have to have a 90% confidence interval. So remember, they always tie together and they have to work out together. So we're going to do a 90% confidence interval using our technology. And so when I do that, I got a confidence interval of negative 24.2 is less than and 3.8. So notice that 0 is in there, and so there definitely could be no difference between the group. So since 0 is in there, we would fail to reject the null, and we end up with the same result as before, that there is no significant difference between the ages of the best actors and actresses. We are failing to reject it. So there's no, we do not have sufficient evidence to conclude that best actresses are younger than best actors. So both of them are giving us the same result, which should be happening at this point. Okay, so go ahead and practice if you haven't already. Make sure you're feeling good about the matched pairs. If you don't understand something, make sure you let me know so we can answer any questions. And with that, we only have chapter 10 left, and we're only doing the first 2 sections. Have a good day.